I'm very happy to talk about my passion for science in that framework. And I have to say, if I was asked if I want to do that, I felt very honored, and at the same time, I was very happy to do so. And then I started and wondered, what should I tell you? Now, talking about one's own passion is not always very easy. Sorry. That's a technical problem. Yeah, sorry, that was a technical issue and I just couldn't change the slides. So let me start by showing you something which is just, you can see a lot on the internet as well. It's a CV. And we heard already that people have different approaches to come to that science. And if you look at my CV, it's actually not the one why I knew from the beginning that I really would like to do science. Actually, I started studying, and when I was doing studying, I was not so sure what to do. For that reasons, I did a teacher's exam in mathematics and physics. And I should be honest, when I started that, my passion was really for mathematics. I did know that I do like the subjects, and to be honest, at that time, I was advised as a female, unfortunately, why don't you go the safe path? Now, when I ended, it became more and more clear that this is not what I wanted to do, and I was offered a PhD in physics, a PhD about bright entangled states and continuous variable quantum communication. I will tell you in a minute what this was, because the way I want to show you my passion for science is that I go over my own CV and show you the development I did along with the science field. I went to Oxford, where I did a postdoc, came back as one Max Planck research group leader, one of this independent research group leader, and then ended up becoming a professor at Paderborn University. Now this sounds very straightforward for you, but let's have a look a little bit closer behind the scenes. And before I do that, I would like to tell you what is the science I'm fascinated about. Because I think if you really want to talk about your passion of science, you should say what is the subject you're interested in. I'm working in the field of quantum technologies, and I believe that many of you have heard in these days or quite heard about that. What is that? It's our goal to harness quantum physics to do new technologies. Now, this is not very new, actually. The so-called nowadays quantum technologies of first generation have already changed our daily life. And the devices or the tools which we have developed are lasers, transistors, semiconductor devices. And there, in order to develop them, we also need an understanding of quantum physics. What we are doing currently is to develop the quantum technologies of the second generation. What we try to do is that we go one step further. We want to harness the quantum properties of individual quantum systems. And I think this is really fascinating. We have really absolute control over these systems. And then we want to do something with that. We want to achieve things which cannot be done with classical systems. And this is why it's so fascinating, why it's at the forefront what we can do there. Now, what is that quantum physics? I know that physicists, you all know it, but let me give you kind of a private view in that. Quantum physics is all about superposition states. The superposition principle, if you think about that, is a very fundamental thing, and it's very awkward and fascinating for itself. It clearly states that a single particle can take simultaneously two different paths if it's not observed. And I like this comic here, where you can see how strange it is. And I should be honest, even showing it to children, they realize that something must be wrong here. But this is what's not wrong. This is the wave-particle duality, which is really old, but modern at the same time. So if you go with single particles through a slit, they behave like waves, which we know very well in water waves. But they also behave as particles, and you see that in these little animations. You see a single dot on the screen, but on the same time, you see the interference pattern. And I should say, this is a very basic principle, but I'm still fascinated by it. And I'm not only fascinated by it, if you think through it more deeply, many famous scientists have been fascinated by that. And here I bring you a citation of Richard Feynman, because I think he expresses quite nicely what we feel in this quantum technology and what a quantum computer or quantum simulator at the end is. He said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." In this statement, you see a lot of things. First of all, if we really want to understand nature, we need probably quantum science. And secondly, it's not an easy problem. As a scientist, it's great if a problem is not easy, because that means you can learn things. Now, I don't want to bore you too much into detail, but I know that physicists are here, and let me try to give a very personal view. What is it? Why is that quantum computer so powerful? It's so powerful because we can simulate large systems, which we can't do classically. And the reason for it is actually rather easy to understand. If you have two just n particles, it's easy to understand that you have 2 to the power of n basis states. And if you want to monitor evolution, you have an exponential overhead. This exponential overhead causes an exponential computational complexity, and thus most systems can't be simulated. And this is also true why it's so difficult to have chemistry, simulation, and so on. And what we try is nothing else but use these concepts, a new logical concept, to really introduce the area of quantum information processing. The fascinating thing is that by now we have come a long path. I'm working not only at Paderborn University this time, but we have also founded the Institute for Photonic Quantum Systems. And there we take these quantum technologies serious. And it really needs an interdisciplinary effort where we combine research from all different fields, from physics, computer science, electrical engineering, to really push the development. And this is what the fascination about that field really has become. At the same time, we are not only developing technology, but we really can learn a lot about fundamental science, and it comes directly as a direct link to applied science. And this is something which I personally find very fascinating, that this quantum photonics allows you to study very fundamental questions, but at the same time to develop a new technology. The vision is that we can establish a photonic engineering within the next 10 years, where we really will see the usage of that, and we will bring this development to all people into daily life. Let me come back to myself. How did it all start? I guess many of you think, okay, these are stories we heard, and this is an introduction to science. But the question is, how is a personal development involved in that? I started my PhD in 1999 and did it to 2002. And I told you already that I was a young student who actually didn't have much experience in physics itself, but I had a huge interest in mathematics. And I also was interested in getting into new topics, and quantum physics I found really fascinating. Now, during that time, and it's interesting, in Germany, there was a very new priority program. And this priority program was about quantum information processing from the Deutsche Forschungsgemeinschaft. And it was interesting because we started a new kind of research area there. By then, we didn't know that. We just saw that we tried to start a new interdisciplinary research area, which really was something new, where we didn't know how successful it would be. But one thing which was already clear there is that the people had very different background. And again, I think this is a nice thing about these Max Planck schools, that we're bridging very different fields. Here you see fields, nuclear spins in molecules, spins of electrons, photons. So this is all physics, but not only physics. We also had impact from information science, algorithms, quantum error corrections, and entanglement. It was great. I was given the opportunity to join the Lois group. And within this priority program, there were many young PhD students and postdocs starting in this new research area. And I should tell you, the people I got to know by then, I still know, and many of them are the friends I'm currently working with. Now, the fascination of the area was, as I told you already then, we came all from fundamental science. And we knew that we want to develop something that we can bring very fundamental questions to applications. Now, what we needed for them was tools from all kinds of different fields. In my case, I was studying ultrafast lasers, fiber optics, homodyne detection, optical setups with classical optics themes, with quantum optics, with quantum mechanics, and then we combined that also with quantum information science. The other thing I really enjoyed, and which I'm still fascinated in that field, optics allows you to have your own experiments, and here you see how these experiments look like. So you build experiments in your lab, and you combine them with theory, which can be really quite intricate. And this theory, basically, you confirm. This is really what physics is about, but it's fascinating to see that and do it on your own and push the field in that direction. Now, here I decided to show you a few old slides. These are actually slides from my PhD time, where I tried as a young PhD student to explain to others what I'm doing. I talked about the statistical character of quantum mechanics, and I told them exactly like I talked to you about the superposition principle, that for a general state, that measurements are not deterministic, and that all kinds of different measurement events can occur. Now, the fundamental property of that is you look for correlations, and for classical correlations, you can have them. Alice receives, we call them Alice and Bob receive statistical results, but we see these correlations, and I think these slides are still illustrative. Now, correlation per se is something which we have a lot, but what we wanted to do is something different. We wanted to study entanglement. And in my case, in my PhD, it was entanglement of continuous variables. And these entanglement are more than correlations, they're quantum correlations. I don't want to go into detail there, but I hope you see from these few sentences already that what was driving me was to understanding something which is so fundamental, which is really questioning what we know from classical world, which is really my fascination for that area. Now, I talked about that, and this seems rather abstract, but you cannot only talk about that, but you can do it in the lab. And these, I showed you the setups in a photograph, but these are measurement results. And if you understood all these concepts and you see the measurement results which nobody has seen before, because this is what you will do in your PhD, you do research at your forefront, it's extremely fascinating. I bring you this graph simply because it was the first graph for me as a PhD student. It was my first publication, and I was extremely proud that I can do it. It was really pushing. It was my first publication which was recognized by the scientific community, and I'd say this is also very rewarding. At the same time, I told you we were already starting to think about applications, and one of the nearest applications, in particular for photonics, was quantum communication. What is quantum communication? Let me say a few words, because I really do like my science, so I like to talk about this science. So quantum cryptography is a system where we have two people who want to communicate, Alice and Bob, and they share a communication system, but not only that, but also a quantum channel. Now, the quantum channel gives you a very specific property, because the operating principle of that quantum key distribution is that quantum information cannot be copied and can be only read once. What this yields, if you make a proper protocol around that, is that you can ensure data transmission between two different points with highest and also long-term security. Here you see one of these properties of quantum systems, how they can be exploited to do something useful. Examples which we nowadays envision are financial transactions, health data, and, well, you can imagine more. Now, this is the status today. This is, again, let me go back to the time when we did that. This quantum key distribution started, I think it's fair, in PB84, so 1984. When I was starting my PhD around 2000, quantum key distribution for continuous variable was brand new. And I was really happy that because it was such a new field, and this is always interesting, that we could be very creative, our own schemes, which were appreciated by the community, and they're still used. For example, using these entangled schemes, which I explored, or also look if you have something which is not perfect, and for our case, it was high losses. This PhD gave me then the opportunity later on to move on. And by then, when I was finishing my PhD, when I was coming to the end of my PhD, I knew I wanted to do science. I was offered a position in Oxford, which was great, and I became a member in Oxford University, but also a fellow of the Wolfson College, which is a community of different scholars there in Oxford, and I had the chance to talk to many other international people. Now, what we did there scientifically is now, as I said, we continued to look for the physics I was just explaining to you, and now I concentrate on single photons. Now, in this slide, again, an original one, you see that it kind of changed already the way we looked at that. We ask, what is it useful for? How can we characterize and how can we make these things? Together with with other scientists, we studied that in Ian Wormsley's group. And we already had at that time the time where quantum-enhanced technologies already had become to flourish. And here in 2001, it was quite exciting because there was a very important protocol how you can build quantum computer with linear optical quantum computation and quantum communication. So we were already aiming for making it more practical. Here, getting it more practical, I was involved in research to use integrated optics for that. And this was the time where I started to have more and more insights what I will do on my own and how I will combine my expertise to kind of find my own field, my own profile. We did also time multiplex detection, so there's very specific detection times. And I should say this time as a postdoc was a very nice time because there you already experience quite a lot and you can follow up your own ideas and you bring in a lot of new topics to the scientific community. After that time, I returned back to my home and I became Max Planck Junior Research Group Leader from 2005 to 2009. For me, that was a quite exciting time because in Erlangen, there was just a new institute, more or less founded, the Max Planck Forschungsgruppe at that time. And I was given the opportunity to create my own first group there. And this is for scientists also quite a new step. For the beginning, you do your own research, then you start to educate others. And I should say, passion for science, I like the subject, but I also really enjoy to work with others and to communicate, to teach others, and to come up with new ideas with others. Do enjoy to work in a group because this is something which is really also very rewarding. Again, the topics, I now started really to see that the system became more complex. We did quantum state manipulation with integrated optics. We looked at integrated sources, and we really pushed more and more towards applications. We looked at quantum statistics, dynamics, and random and in quantum walks. I don't want to go into detail there, but we are going more and more towards the direction of quantum simulations. In 2010, then finally, I got an offer at Paderborn University. And at that time, I knew a lot, I had learned a lot, and now I had my own group already, and now I wanted to do something even more applied. I wanted to make a difference in these things, and it became clear that quantum technologies became more and more a topic where we really can do something, and we have to develop the technology for that. Now, let me say a few words to Paderborn universities because some of you will also meet fellows from that place. And probably it's also interesting what kind of places are there in Germany. Paderborn University is a historic town, a medieval town with a cathedral and a river. But this was not the reason why I went there, although I enjoy being there, and I really also enjoy this kind of atmospheres there. One thing which was already at Paderborn University was an on-site nonlinear waveguide fabrication facility. And this was important for me. I really wanted to be able to fabricate my own devices, to come up with their own designs, and really do something more than just building that up or on an optical table to become more and more applicable and practical for applications. Now, the topic which I was since then pursuing, and actually it was a direct continuation from what I explained to you earlier was really the idea of building up quantum networks. Why quantum networks? What is that quantum network is about? Why I'm fascinated by that? A quantum network for me is a model system. A model system where you can see that you have a lot of different sides. These different sides are connected. In our case, these are photons which are traveling from one place to the other. And altogether, they build a rather complex large-scale structure. Now, such structures you will find in all kinds of different scientific areas. The quantum internet, of course, you probably have heard about that, is one thing. And quantum communication, what I just showed you with quantum security, is one way to look into that. And it's certainly fascinating for itself. But it's not only that. We can use that also as a model system for studying completely different things. We can try to understand how is actually transport gathered. And if you're talking how that is, how does quantum physics really impact this transport? So other example is brain, neurons. If you look at the brain, we have classical computational models for them, for sure, and we use computers for that. But the question, is that all, or is there more? Well, there is probably more than what we see currently, because quantum physics, I just told you, is still something which impacts, and it's still hard for us to do that with the computers. So here, although, and I told you that we are becoming more and more applied, the fundamental science is still there. And it's still driving my own passion for science. I want to understand of quantum physics in such complex, large-scale structures. Now, if I go a little bit more directly, what does that mean for photonic quantum systems? It means that we can build nowadays quantum computation and simulation devices. Here on this photograph on the left, you probably can see that it's still not easy. And it's still not easy, not only from the experiments, which are still at its infancies. It's also not easy because we do not quite understand what we really want to do. And this is probably hard for you to understand. The quantum computer, you hear it will be a quantum revolution, and I believe in that. But what kind it is and what this science will bring to us, for me, it's not clear at all. But we can be the ones who invents new ideas and pushes the field. And this is really something which is extremely fascinating. It's not only about computation and simulation. There's metrology. What does metrology mean? This means the limits we can measure things. And you see again that this is very fundamental for itself, but it's also very important to measure very small things with super resolution, with, well, all kinds of different things is equivalently an important field. And last but not least, we're talking about photons. Sorry, I don't know what. Can you help me?
Der Klicker funktioniert wieder nicht.
Okay.
Okay,
so let's try. Sorry for that. Apparently there was another problem. For quantum communication, we have made a big progress, and nowadays we really also can look for more advanced formats, but not only advanced formats. We're talking about high-dimensional information encoding, where temporal modes of pulsed light, so we're looking at pulsed photonic systems, also play an important role. Now, if you want to build such a system, and you really want to make something to build up a whole technology, it's not easy. Here, you see my group. Well, you don't see my group, but you see kind of the logo which we developed during my time when I just started my group, the Integrated Quantum Optics Group. Coming to Paderborn, I wanted to have a different ansatz, a different way how we want to do that. I was going there because I wanted to have an own technology. That means I wanted to work together with people who really knew how to fabricate things for tailored quantum applications. And this brings an own area for itself, the technology of integrated photonics. Now, to make progress, you want to fabricate something specific. Yes, not fabrication just for having nice fabrications and to fabricate nice structures. We want to build devices from that. Devices which can be used in the upcoming technologies, quantum devices. Optical circuits, we need to model them. And here you see the buzzwords of what we are doing here. And last but not least, we want to build up quantum networks. Well, this sounds very technical, but this is where I was coming from. I want to investigate at the end fundamental science, but not only fundamental science. I want to apply them for real applications. Now here you see already that all these different fields have very different tools, and it's fascinating to work together and bring people together who really work on these different fields. Here you see 3 of my group leaders who really helped me here, because not all expertise which you need for what you want to accomplish can be done by a single person. It's important that people work together. And this is why in the group we have these different fields which work together and we're using very different methods. Now, the group is much larger than that. And I really want to acknowledge the people who are working with me. It's great fun to work with these people. They really come from different background. They're all physicists, but they're interested in different things. And here you see a typical slide where typically I end my presentation with. It's very important that you say thank you to all of these people. And I also want to say it here, because at the end, my passion for science and what I want to achieve is only doable because a lot of people work with me. And if I talk a lot of people, this can be students, which are really young students, and it's really makes a lot of fun. It's enjoyable to work with students who have just started studying. And I really would welcome also people to look into the different groups. And these young students are quite frequently the most open-minded people. You should preserve that for yourself. Asking questions which you might seem to be stupid or just unexperienced is very important, because the more senior people, be it the PhD students, which many of you are, or be it then also the postdocs, sometimes say, oops, we haven't thought about that. It's very important to have these inspiring questions from very young people. On the same time, as a PhD student, you start to take over responsibility for the younger students, and you become more and more an advanced scientist. And I showed you here my own path, how I was a rather young PhD student, and then over becoming a postdoc, helping with other, developing the ideas, and then a group leader, and then a professor. This whole working together with these other of different people on different career stages is a fascinating thing which we have in academia, and I would not like to miss it. Finally, I would also like to now look a little bit around about the Max Planck School, the Max Planck School of Photonics in my case. I talked about my own career, how I was really, getting to this career, and how much I enjoyed working together with my group. But this is not the end. I think the Max Planck School of Photonics, and it's a real strength, also has very strong collaboration. I think it's in all Max Planck schools. And this is for me the fascination of it, because we now can really connect to each other and we can do things which the individual groups can't do. And you, as a new member of these Max Planck schools, have the opportunity to really have context and be experienced or exposed to expertise from all these different places. And I should say that this is really something which brings something really new. In our case, it gave us the opportunity to really come to the idea. There's an initiative from the German government that we can build a photonic quantum computer. An individual group couldn't do that. But if you build a consortium where everybody contributes, we really can do something which is rather large, and this is then fascinating per se. In quantum photonics, we want to demonstrate a quantum advantage, and we want to collaborate and build algorithms on that. And it's quite frequently not only academia, but it's also connecting to industry. And the goal is really now to build such a machine that we can demonstrate the photonic quantum advantage, which is kind of the essence of a quantum computer, by 2025. With that, I'm at the end. I would like to thank you for your attention and happy to take questions.
Thank you, Professor Silberhorn. Yes, now I'm on the way. And there is a lot of questions coming up. And I would like to ask the first one, which is, from your experience, for example, at Oxford University, what could German science learn from other countries when it comes to diversity?
This is a good one. I didn't talk about diversity per se, but I'm happy. Thank you very much for that question, because I think sometimes it's interesting to see the CV first. What we can learn is that we don't care so much about the gender. That sounds very easy, but if you go to Oxford, this is a place where really I felt very free. It was the community and the joint expertise of these different people, different scientists working together and concentrating on the topic instead of other issues was very strong there. Now the question is, how can we learn from that? I think the important thing is try to get together in an informal way and discuss these things, because I experienced a very open society in that. And I told you that I was fellow of the Wolfson College, where we had regular meetings between fellows of all different disciplines with an evening where we had sponsored wines and we discussed together. And I think these kind of events that you really meet together is very important.
Okay, and there's another question. How did you deal with delayed gratification? For example, getting recognition for a paper only years after it was published in the early years or in the early stages of your career. How did you do that? Shall I ask a question again?
Yes,
it's a very long question.
It's a long question, and I just needed some time to answer, because I was not sure whether I really experienced that so much as a problem. Sorry for saying that, but at that time, sometimes it's important that you try to concentrate on what you are doing and how you talk to people. For my case, the community was small enough that I was given the opportunity to go to conferences, to present my ideas and to talk to others. And I should be honest, during my PhD, I was not so much worried about publications. I think this was really something which is now, I understand that it's more and more pressing for the people nowadays, for the PhD students. But I only want to say, try to concentrate on your science and the publication will follow, although I understand that this is not easy. Having said that, I think for young PhD students at the moment, there are many opportunities which will open up for you, and people do not look so much for publication as you might think.
Okay. You moved from fundamental research towards more and more specific and advanced projects. At the crucial points, how did you decide which ideas to pursue?
I looked what I wanted to understand and to do. It came, and this is why I tried to show you, it came in a natural way. I was fascinated by the fundamentals, and then I wanted to do more. And then I wanted to see, but what is it what I want to understand? This is why I talked about these networks, and I asked myself, what do I need? And then I understood more and more that what I need is really technology. And this was my driving force behind these decisions.
Okay. There's another question from the audience. That is, did you or your friends in science experience imposter syndrome? If so, what advice would you give in dealing with it?
What do you exactly mean by that?
That's a very good question, which I can't answer because it's a question from the audience.
Yes, I know.
Probably.
I'm not so sure.
Okay, the one who's asked this question, perhaps he or she can just formulate it in a different way. And we go over to the next question. That is, what would be your advice to the students who are about to start their PhD? You kind of gave some answers already.
The advice to start your PhD is do something. First of all, when you start your PhD, do something which you're really interested in. Don't do it because you think that this is a good thing which will be successful. Now, I told you that I started in that priority about quantum information. At that time, people were, yeah, it's exciting, but it was not, well, it was modern, but it was not something like where people really said, this will be the future. I was fascinated by that because I saw a possibility. I had a mathematical background. I was interested in these concepts. I was also interested by the experiments, and I wanted to do that, and I liked optics. And this is the best advice. You must like what you do. This is a very simple advice, but if you try to do it because you want to be successful, I think this will not work.
Okay. And how do you deal with setbacks in your research? For example, delays due to external factors, to COVID-19 or whatever. And how do you stay motivated?
This is a tricky one. And I should be honest, setbacks will always be there. This is also part of becoming more senior. Becoming successful means that there will be things where I say, I can't continue on that path, I'm frustrated. And should be also honest, all of you also ask yourself, how can I make a career? And also for myself, it was not always clear, also from private life, how I could manage all this while moving from one place to the other. Stay motivated is, again, try not to think so much by it and try to see that the motivation why you do that, did you remember it? This is why I said, please do something what you like. This makes it easier.
Thank
and
you.
The setbacks.
No, go on if you like.
The setbacks, you must just take them as part of the story. If you're through, then quite frequently you're even stronger. And this is what you have to learn.
There's another question. What made you join the Max Planck Schools as a fellow? Why did you do that?
I tried to answer that because it's an extremely strong network where we really have experience from very different fields. This is something which I learned more and more during my career, that it's very important that you're not doing only the science in your little chamber, but you need really the influence from a lot of different sides. And there the Max Planck School is a unique opportunity for research, for education. It's just great. There's so many different expertise which you can really use there. This is fascinating.
Okay, we've got one last question. No, we've got a definition for the imposter syndrome that is loosely defined as doubting your abilities and feeling like a fraud. I think the question was, how do you deal with feeling this syndrome?
I don't know. Yes, there are the feelings where you just don't feel to be taken very serious. But at the end, maybe the professional life is not everything. If people don't treat you like that, it's up to you to say who you are. And even if things don't work out, if somebody else thinks you're not great, so what? I think it's very important that you stay confident with yourself.
Thank you. We've got one last question that kind of leads over to the topic of the next point. How do you try to increase diversity in your team and at your institution?
Well, I think one of the things I have it's somehow more easy in my case. I'm female, and there are not too many female professors. But this answer would be probably too easy. But I should say this is something I get a lot of applications. But I should say there's real measures which I also take. So what I think which is important is that you try to contact young female students or diversity in general, already when they're pretty young. This helps. Also, we had it about the question about self-confidence. We take the young students, I talk to them personally, and I think this is very important, and encourage them, because it is true. Unfortunately, it's still true that a lot of female students are not as confident with what they can do, what they can achieve. They're quite frequently really excellent students and don't believe it. So I try to help them and really encourage them with personal meetings. This is very important that you have a personal contact. This is, I think, true in general, that you try to have a personal relationship, and I really enjoy that. But it's probably even more important for diversity.